In the last part of this chapter, we are going to go through various problems in which we utilize the relationship between the stress and the strain. Given a state of strain, we find the stresses, or given the state of stresses, we find the strain. For linear elastic materials, isotropic or orthotropic or transversely isotropic. However, the first problem is used here, or is presented here, to explain why we have imposed the restriction that when the stresses are written as functions of the strains, or when the strains are written as functions of the stresses, this applies to the relationship and its inverse. We have imposed the restriction that this constant, which relates C11, so this is C11, 11. The constant that relates sigma 11 with epsilon 22, we said has to be equal to the constant that relates 22 with epsilon 11. So we said that this has to be symmetric. And this problem explores why does this matrix of coefficients need to be symmetric. And we said at the beginning of this chapter that this is symmetric so that the energy, so that the material would not dissipate or create energy during cycles of loading. So let's explore the idea. Let's try a material. Let's read what this problem states. So we're trying a material where the relationship between the strain and the stress is not symmetric. The coefficient here is different from the coefficient here. We have different Poisson's ratios. And we're going to take this material and cycle it through a state of stress. We're going to pull it with sigma 1, and then we're going to add sigma 22, and then, so we're going to start from 0, pull it in sigma 1, then pull it in sigma 22, and then remove both stresses and go back to the state of 0, and calculate the energy that's taken or created or dissipated through this process of loading and unloading. So in this problem, the symmetry of the coefficient matrix will be shown to be crucial so that the material model would not predict energy creation or dissipation during loading cycles. So we're assuming a linear elastic material specimen is loaded through the following 3 steps. Step 1, sigma 1 goes from 0 to 100 MPa. Step 2, sigma 1 is equal to 100 and stays 100, while sigma 22 goes from 0 to 100. Step 3, sigma 1 goes from 100 to 0, and sigma 22 is equal to sigma 1, also goes from 100 to 0. And the relationship between the stress and the strain is given by this. Say epsilon 1 is equal to sigma 1 over E minus 0.3 sigma 22 over E, and epsilon 22 is given by this relationship and the 2 different Poisson's ratio, making the matrix not symmetric. So we're going to calculate the energy here, and we're going to show that this energy is actually dependent on those 2 Poisson's ratios. Okay, so let's go through the first loading step. In step 1, sigma 1 goes from 0 to 100, and sigma 2 is equal to 0. The energy that's going into the deformation is equal to sigma 1, the integral of this integral, sigma 1 d epsilon 1, when epsilon 1 goes from the state of sigma 1 equals 0 to sigma 1 equal 100, plus the integral of sigma 2 d epsilon 2. Now we know that sigma 2 in this case, this is 0. And we know that epsilon 1 is equal to sigma 1 over E minus Poisson's ratio sigma 2 over E minus all these are zeros, which means that the rate of change of epsilon 1 is equal to d sigma 1 over E. So U, the energy, is equal to sigma 1. Instead of d epsilon 1, I'm going to use d sigma 1 over E, and sigma 1 changes from 0 to 100, which gives me sigma 1 squared over 2E, which is equal to 100 squared over 2E. The energy in step 1 from 0 to 100 is equal to 100 squared divided by 2E. Now what's the energy that goes, or that's either consumed or released in step 2? In step 2, sigma 1 starts at 100 and ends at 100. Sigma 2 starts at 0 and ends at 100, and all the units are in MP. Again, the energy in step 2 is equal to the integral of sigma 1 d epsilon 1, where sigma 1 is equal to 100 and goes to sigma 1 equal to 100, plus the integral when sigma 2 equals 0, sigma 2 equal 100 of sigma 2 d epsilon 2. Now I'm using stresses, so I'm going to replace those with stresses. I know that epsilon 1 is equal to sigma 1 over E minus Poisson's ratio sigma 2 over E, but which Poisson's ratio? Yep, it's the negative 0.31. It's the negative 0.3. And I know that epsilon 2 is equal to sigma 2 over E minus 0.4 sigma 1 over E, which means that the increment in epsilon 1 has to do with an increment of t sigma 1 minus 0.3 and increment of t sigma 2. And similarly, the increment in epsilon 2 is equal to an increment in sigma 2 minus 0.4, the increment in d sigma 1 over E. Alright, so I'm going to replace d epsilon 1 and d epsilon 2 with increments of the stress, because I know that the bounds of my integral are in terms of the stress, so it would be easier for me to do the integration. So I'm gonna sigma 1 equal 100 to sigma 1 equal 100. Sigma 1 multiplied by d sigma 1 over e minus 0.3 d sigma 2 over e plus from sigma 2 equals 0 to sigma 2 equal 100. Sigma 2 instead of d epsilon 2 I'm going to use the increment in the stresses. Which I'm going to write as follows. From sigma 1 equal 100 to sigma 1 equal 100, sigma 1 d sigma 1 over e minus from sigma 1 equal 100 and sigma 2 equals 0 to sigma 1 equal 100 and sigma 2 equal 100. I'm going to use 0.3 sigma 1 d sigma 2 over e plus from sigma 2 equals 0 sigma 2 equal 100. I'm using sigma 2 d sigma 2 over e minus when sigma 1 equal 100 sigma 1 equal 100 sigma 2 0.4 d sigma 1 over e. When you compute these integrations, d sigma 1 goes from 100 to 100. This will be equal to 0. And when you also calculate this last d sigma 1 is 0, you'll also find that this is equal to 0. And you're going to be left with those two integrals. And the second one will give you sigma 2 squared over 2e minus 0.3 sigma 1 which is 100 and sigma 2 over e, which will be equal to 100 squared divided by 2e minus 0.3 100 squared divided by 2e, divided by 1e. In this last step, sigma 1 d epsilon 1 plus sigma 2 d epsilon 2 and here sigma 1 goes from 100 to 0 and sigma 2 goes from 100 to 0. So I'm going to utilize that sigma 1 is equal to sigma 2. Which means that d sigma 1 is equal to d sigma 2. And instead of d epsilon 1, I'm going to utilize the relationship above. So this is equal to sigma 1, d epsilon 1 is equal to d sigma 1 minus 0.3 d sigma 2, but they're the same, so I'm going to use d sigma 1 plus, again in sigma 2 I'm going to utilize sigma 1 because they're equal, and instead of d epsilon 2 I'm going to use d sigma 1 over e minus 0.4 d sigma 1 over e. And in this case I'm only integrating over sigma 1. Because I'm only integrating over sigma 1, I'm going to use the bounds of sigma 1 from 100 to 0 and from 100 to 0. This will be equal to 0 minus sigma 1, which is 100 squared over e. So negative 100 squared over 2e minus 0.3 over e. 0 minus 100, which is plus 100. Plus 0 minus sigma 1 squared over e, which is basically net minus 100 squared, again divided by 2e, plus 0.400 divided by e. Okay, so we have three values of energy through step 1, step 2, and step 3. Step 1 is loading, step 2 is loading, step 3 is unloading. So let's sum u total has to be equal to u step 1 plus u the energy from step 2 plus the energy from step 3. So if you add all the above together, you will find that the total u will be equal to the following: 0.4 minus 0.3, 100 divided by e, which is one Poisson's ratio minus the other Poisson's ratio. Actually, this has to be squared. The first Poisson's ratio minus the second Poisson's ratio. I expect this to be equal to 0. So why is it not equal to 0? The reason why it was not equal to 0, even though I loaded the material and then unloaded it, the reason was because these two values were not equal, because the material did not have a symmetric relationship between the stress and the strain. So we need the symmetric relationship between the stress and the strain to ensure that when I load the material and then unload it, I do not have energy created nor destroyed. Of course, I cannot have energy created, because if I have a material that when I load it and unload it, I get energy from this material, then I found then this material all I have to do is just put it in a car, load it and unload it. Every time I load it and I load it, I can extract energy from it, and I don't need any forms of energy creation anymore. I can just use this material to create my energy. But in general, a linear elastic material cannot create nor dissipate energy, and therefore the material model has to predict that the energy created or dissipated is equal to 0 when I load and unload the material. Alright, so the purpose of the first problem was to show why the relationship between the stress and the strain has to be symmetric, why the matrix of coefficients that relates the vector of stresses and the vector representation of the strains have to be symmetric. In the second problem, we are trying to find the relationship. We're utilizing the relationship between the stress and the strain to find the stress inside an object. So given a state of strain inside a continuum represented by the small strain matrix given by those 6 numbers, and I say 6 because of symmetry, and assuming that the material is steel, given Young's modulus and Poisson's ratio, therefore linear, elastic, isotropic, and it follows the von Mises yield criterion with sigma maximum equal to 750 MPa. So the check chapter 2, what this says is that given a stress matrix, I can calculate the von Mises stress of that stress matrix, compare it with 750, and see whether this material has yielded or not. So the question: find the principal strains, find the principal strains directions, find the principal stresses, their directions, and comment on whether this state of strain is possible or not. So To find the principal strains, all you have to do is just write eigensystems in Mathematica of the strain, and you will get the principal strains, which are the eigenvalues, and the principal strain directions, which are the eigenvectors, or the normalized eigenvectors. And then we need to find the stresses. Now, the relationship between, let's just look at the relationship between the stress and the strain in a linear elastic isotropic material. The relationship between the stress and the strain in a linear elastic isotropic material is given by this matrix. Either this one, which relates the strains to the stresses, or this one, which relates the stresses to the strains. I know the strains. I input the strains into this relationship, multiply it by this huge 6x6 matrix, and find my stresses. The only thing that you have to be very careful when you do it is that the vector representation of the strain has the following: epsilon 1, epsilon 2, epsilon 3, 2 epsilon 1, is equal to 2 multiplied by 0.001. Don't forget the 2. Epsilon 3 and 2 epsilon 2, epsilon 1, epsilon 2, epsilon 3, epsilon 2, epsilon 3, epsilon 2, 3. Now to calculate the stresses, which is equal to sigma 1, sigma 2, sigma 3, sigma 1, sigma 1, sigma 2, 3, those vector representation of the stresses, I need a 6x6 matrix, and I will show you in a different video how to do this quickly in Mathematica. And you put the strains here, the 6x6 matrix multiplied by 6x1 vector, you get your stresses. And when you do this calculation, you get the stress matrix, you get the stress vector, and you can make it into a matrix. And the numbers are going to be 383.7 MPa, 161.5, 323, 161.5, negative 424.0, 161.5, it's symmetric, 302.9, so symmetric. And the von Mises stress, of course you can calculate the eigensystem of sigma, find that eigenvalues and the eigenvectors. The von Mises of the von Mises stress is equal to a huge equation, check chapter 2, which is equal to 1031.19 MPa. So what does this tell us? This is much bigger than the maximum, which means that this state is not this state of strain, is not possible, because it predicts a stress that is higher than the maximum. It predicts a von Mises stress that is higher than the maximum stress that the material can actually take. In the third problem, we have a plate that has dimensions 2 meters and 1 meter. And the plate looks like this. It has 2 meters in this direction and 1 meter in this direction. This is E1, this is E2. And the bottom left corner coincide with the origin of the coordinate system. And I'm given a non-homogeneous deformation, a non-linear deformation. The only thing is that the position in x3 stays the same. So the position perpendicular to the plate does not change. This is the position in the horizontal direction. It changes. The position in the vertical direction changes. The position in the third direction does not change. Show that this is a state of plane strain. Okay, well, check chapter 3. How can you find the strain? To find the strain, first you have to calculate your displacement vector, u1, u2, u3, and the displacement vector is equal to the new position minus the old position, which is equal to 0.001 capital X2 plus 0.0002 x1 squared. That's when you calculate x1, small x1 minus capital X1. Small x2 minus capital X2 will give me 0.001 x2 minus 0.0002 x2 squared. x3 minus x3 is 0. Okay, how do you calculate the strain? The strain is calculated using, first we have to calculate the gradient of u, which is a matrix made of partial u1 by partial x1, partial u1 by partial x2. And so on, which, when you do all these calculations, you're going to get 0.0004 x1, 0.001, 0, 0, 0, and a 0 here, and 0.001 minus 0.0004 x2. Okay, so the strain, the small strain, is equal to the gradient of u, 1 over 2, plus this matrix gradient of u, but the transpose of it, which gives me half a matrix. You're going to find a value here, non-zero value, non-zero value, non-zero value, non-zero value, and then 0, 0, 0, 0. Indeed, it's a state of plane strain. Indeed, epsilon 1 and indeed epsilon 1 3 equal to epsilon 2 3 equal to epsilon 3 1, of course, because of symmetry, epsilon 3 2 because of symmetry, equal to epsilon 3 3. All those are equal to 0. The only non-zero are epsilon 1 1, epsilon 2 2, and 1 2. And the green strain matrix will be equal to half the gradient, this matrix, plus its transpose, plus this transpose matrix multiplied by this matrix. And so we can calculate engineering small strain matrix and the green strain matrix and show that the engineering small strain is adequate to describe the motion, you will find that the difference between those, the small strain and the green strain, will be very small. Difference between E small and E green will be very small. Then plot the vector plot of the displacement function. I will show you this using Mathematica on the plate. And the next thing is, okay, now we have the strain. So this, all what we've done so far is what we learned in chapter 3. The next step is, what's new in this chapter is how to calculate the stresses. Given the strains, given the deformation, given the strain, given the deformation, we need, and given Young's modulus and Poisson's ratio, and assuming it's linear, elastic, isotropic materials, we need to find the equilibrium body forces. To find the equilibrium body forces, we need to find the stresses first. What are the stresses? After finding the stresses, we can use the equilibrium equation to find the body forces, and then from the stresses we can find the von Mises stress and the out of plane stress components. Given E, I can find the stress as a vector because I know the 6 by 6 matrix multiplied by those strains, which I already found. So I know the stresses, and given the stresses, you'll find that the stresses I'm going to form the matrix from the numbers that I'm going to get. And I'm going to utilize the equilibrium equations because this will be function of the position. It's a non-linear relationship for the strains, and so the stresses will be functions of the position as well. And so from the equilibrium equations, you'll be able to calculate partial sigma 1 by partial x1 plus partial sigma 1 2 plus partial sigma 2 1 partial x2 plus partial sigma 3 1 by partial x3, and I'm using small x1, x2, and x3, but I can use the capital ones because it's small deformation, plus rho b1 equal to 0. Calculate those components. And the von Mises stress, I can calculate it using the big equation, which we already know. And again, I'm going to show you this using Mathematica in a different tutorial. In the next problem, usually these kinds of problems are appear in soil mechanics, where you get a soil specimen, you put it inside a container, and you apply what is called a confined compression test. In the confined compression test, you put stress in circumferential or confining pressure. So the confining pressure is given as negative 500 MPa, while the vertical stress is given as negative 100 MPa. And then we have the strains in this direction: epsilon 1, 1, epsilon 2, 2, and epsilon 3, 3. we need to find Young's modulus and Poisson's ratio. Okay, so the stress matrix is given by 100. Sorry, sigma on 1 is negative 500. Sigma 22 is negative 100. Sigma 33 is negative 500. And the strain is given by epsilon 11 is equal to negative 0.003. No shear strains. Epsilon 22 is equal to 0.001. Epsilon 33 is equal to negative 0.003. And the purpose of the experiment is to find Young's modulus and Poisson's ratio, assuming that this is a linear elastic isotropic material. Okay, epsilon 11 I know is equal to sigma 1 over E minus Poisson's ratio sigma 1 over E. So I know that negative 0.003 is equal to negative 500 over E minus Poisson's ratio. Sorry, this is the relationship between the strain epsilon 1 and the stresses. Epsilon 1 is equal to sigma 1 over E minus Poisson's ratio sigma 22 over E minus Poisson's ratio sigma 33 over E. So, by substitution, this is epsilon 1, this is sigma 1, and sigma 22 is 100, or negative 100. Sigma 33 is 500, plus Poisson's ratio 500 over E, which tells me that negative 0.003 E is equal to negative 500 plus 600 Poisson's ratio. This is equation 1. The second equation is epsilon 22 is equal to sigma 22 over E minus nu or Poisson's ratio sigma 1 over E minus Poisson's ratio sigma 33 over E. So I can write the second equation as epsilon 22 is equal to 0.001 equal to sigma 22 over E minus Poisson's ratio sigma 1 over E minus Poisson's ratio sigma 33 over E. From here I get equation 2, which tells me that 0.001 E is equal to negative 100 plus 1000 nu. This is equation 2. Two equations in two unknowns. Solve and you will find that the value of Poisson's ratio is equal to 0.222 and the value of Young's modulus is equal to 122.22 MPa. And the purpose of this problem is you take a specimen, you take it to the lab, you put known stress, you calculate the strain, and from this you calculate your Young's modulus and your Poisson's ratio of that specimen. In the next problem, we have a transversely isotropic linear elastic piece of material, with the isotropy plane being the plane of E1 and E2. So let's visit the relationship between the stress and the strain in a transversely isotropic material. In a transversely isotropic material, the relationship between the stress and the strain is given by this 6x6 matrix. And the unknowns or the material constants are given by those. Okay, so this is the relationship. Now, and I have to make sure that it's the same axes. The axis of symmetry for this relationship is axis of symmetry is E3, and plane of isotropy is E1 and E2, the plane with E1 and E2, and so this is exactly the relationship that we need for our material. And we already have, in the plane of isotropy, I have E equal to 100 MPa, and Poisson's ratio is equal to 0.2. In a uniaxial tension test, when the material was stretched in the direction of E1 by a stress value of 1 MPa, what happened? The strain measured in the direction of the vector E3 was recorded to be this. So epsilon 33 in this case was equal to negative 0.30005. And when the material was stretched in the direction 3, sigma 33 is equal to 1 MPa, what happened? The strain in the direction of E3, again, epsilon 33 was equal to 0.002. And we need to find E33, Poisson's ratio 1,3, and Poisson's ratio 3,1. Okay. So I'm gonna, if you look above at the relationship between between the stresses and the strains, so I'm gonna start with the second case and utilize the relationship above. So from the second case, I know that epsilon 33 is equal to sigma 33 over E 33 minus Poisson's ratio 1,3 sigma 1 over E minus Poisson's ratio 1,3 sigma 2 over E, but these are zeros, and I'm left with epsilon 33, which is 0.002, is equal to 1 divided by E33. From here you can get a value for E33, which is equal to 500 MPa. From the first case, we know that epsilon 33 is equal to sigma 33 over E33 minus Poisson's ratio 1,3 sigma 1 over E minus Poisson's ratio 1,3 sigma 2 over E, and again this is given as negative 0.0005, and I know in the first loading case I only have sigma 1, so this is 0, this is 0, and E is given as 100 MPa, so negative sigma 1,3 multiplied by 1 over 100 MPa equal to negative 0.0005, and from here negative Poisson or positive Poisson's ratio 1,3 will be equal to 0.05. Okay, so I have E33 and I have Poisson's ratio 1, 3. What is Poisson's ratio 3, 1? Let's go back to the relationship just to show you how to calculate those. The other Poisson's ratio. I'm going to look at the relationship between the stress and the strain in a transversely isotropic material. And where does mu31 appear? Mu31 appears right here. And here's mu13. I'm going to utilize that this relationship is symmetric. Because this matrix is symmetric, I can relate this value to this value. So, going back to the problem, mu13 over E is equal to mu31 over E33, and you can find the remaining Poisson's ratio as 0.25. We have a few problems left. In the next problem, we want to see the effect of changing the directions of our orthonormal basis vectors. So if we change our basis vectors of our vector space, what happens to the relationship between the stress and the strain? So for linear elastic material, we expect that nothing happens. If I have, because it's linear elastic isotropic, for linear elastic isotropic materials, under any coherent system, the relationship between the stress and the strain stays the same. But this is not the case for other kinds of materials or other types of materials such as orthotropic or transversely isotropic materials. Because for transversely isotropic and for orthotropic materials, the relationship depends on the direction or on the direction vectors that you're using for your basis vectors. So for this problem, we are considering an orthotropic material whose major axes of orthotropy lie in the direction of the vectors E-1, E-2, E-3. So everything is happening in this basis. All the relationship between the stress and the strain is given in this basis set. So when I write the relationship between the stress and the strain, I'm writing the relationship between sigma prime and epsilon prime. I'm not writing the relationship between sigma and epsilon. So the material properties in the coherent system defined by the orthotropy axes, which are given by E-1, E-2, and E-3, are given by E11, E22, E33, Poisson's ratio 3,1, 3,2, 2,1, G12, G13, and G23. And now we have a new coherent system defined by the basis set B. It's equal to E1, E2, and E3, where E1 is the traditional 1, 0, 0, 0, 0, 1, actually 0, 1, 0, and 0, 0, 1. If the material is in a state of a uniaxial stress, such that the only non-zero stress component is sigma on 1. So in this coherent system, the stress looks like this. Now we need epsilon and we need epsilon prime. Now we know that the relationship is given here. I know that epsilon prime is given as a function 6 by 6, C above, multiplied by those prime components of the stress. But we have these components, sigma, which is equal to sigma on 1, 0, 0, 0. So the first thing we have to do is find those sigma prime components. Now the sigma prime components, if I have a translation vector, a translation matrix from this coordinate system to this coordinate system, where Q is equal to E-1, E-2, E-3, 1 over root 2, 1 over root 2, 0, negative 1 over root 2, 1 over root 2, 0, 0, 0, 0. I know that the relationship between the stresses and the strains in those two coordinate systems are given like this. Sigma prime is equal to Q sigma Q transpose. Epsilon prime is equal to Q sigma Q epsilon Q transpose. From this, find sigma prime. Find sigma prime, put it here. After finding sigma prime, then find epsilon prime given sigma prime from relationship between epsilon prime and sigma prime. I know the stresses, the prime stresses, I get the prime strains, and the original or the strains in the non-primed coordinate system can be found using the relationship because epsilon prime is equal to Q epsilon Q transpose. If you multiply it by Q epsilon prime, so Q transpose epsilon is equal to Q transpose Q epsilon Q transpose, Q transpose epsilon prime Q will be equal to epsilon Q transpose Q, which is equal to epsilon. And so just using matrix manipulation you can find the required in this problem. And again, I'm going to show you in using Mathematica how to solve these problems by just simply multiplying the matrices. So question number 7 is a direct application of plane, direct application. Of plane stress and plane strain. Strain equations, which is the which is given with just a more simplified version of the relationship between the stress and the strain. It relates 3 components of the stress with 3 components of the strain, because most of the stresses and the strains in plane problems, most of the components are equal to 0. So I'm able to modify the relationship and make it into a 3 by 3. The relation that I relate 3 strains to 3 stresses, and I use a simpler version of the constitutive law. Problem number 8. the in-plane displacement of a plate of a dimensions 5 meter and 1 meter in the direction of E1 and E2 respectively is given using this relationship, assuming that U3 is equal to, we don't know what U3 is. We're just assuming that this plate is in a state of plane stress. We need to draw the contour plot of the change of the thickness of the plate, which means there is a U3, there is delta T, because there is epsilon 33. We know the Young's modulus is given, Poisson's ratio is given, and the thickness of plate is given. Okay. So how are we going to do this problem? The first thing we have to do is calculate what we know about this is a state of plane stress. Plane stress means the stress matrix has sigma 1, sigma 1, 2, sigma 1, 2. These are non-zero values, and the rest have to be 0. And the strain is equal to epsilon 1, epsilon 1, 2, epsilon 1, 2, epsilon 2, 2, 0, 0, epsilon 3, 3, which is currently unknown, 0, 0. What I know is U1 and U2, so I can calculate the gradient of U, which is partial U1 by partial X1, partial U1 by partial X2. And I'm only going to calculate the first 4 components. And calculate the strain as half the gradient of U plus the gradient of U transpose. When I do this, I'm able to calculate those 4 values of the strains. Given those 4 values of the strains, this is a state of plane stress, so I know that the relationship is as follows: sigma 1, sigma 2, 2, sigma 1, 2. In a state of plane stress, if you go to the top and look at the relationship between the stress and the strain in a state of plane stress, it's given by the following: 1 over 1 minus Poisson's ratio over 1 minus Poisson's ratio, 0, 0, 1 over 2, 0, 0, Poisson's ratio divided by 1 minus Poisson's ratio, 1 over 1 minus Poisson's ratio, multiplied by those values that you have, epsilon 1, 1, epsilon 2, 2, epsilon 1, 2, which are given as 0.02 plus 0.02 x2. (0.02 plus 0.0015 x1 squared), and you can calculate epsilon 2 as well. So given those, I now have values for sigma 1, sigma 2, 2, and sigma 1, 2. And when you look at the relationship between the stress and the strain for plane strain case, you get, for plane stress case, you also get an additional relationship that gives you what the value of sigma 33 is. Sorry, epsilon 33. Epsilon 33 is equal to negative Poisson's ratio sigma 1, 1, negative Poisson's ratio over E, sigma 1, 1 plus sigma 2, 2. So basically, I have a plate. The plate deforms. It's in a state of plane stress, which means it's allowed in the thickness direction. It's allowed to deform, contract, or expand. And since it's allowed to expand or contract, this epsilon 33 has a value. And this value, because the deformation is non-linear, the deformation is not constant across the plate, this epsilon 33 is function of the value of the position of the plate, and so this will be function of x1 and x2, position of the plate, and given epsilon 33, this is small strain, is equal to delta thickness divided by thickness. And so delta T can be calculated from this problem right away. And again, I'm going to show you using Mathematica at some point how to solve this problem. The last problem that we're going to go through today, and which concludes this chapter, is a problem related to pressure vessels. Problem number 9. And for details, you can view your textbook, because all these problems are solved in details in your textbook. So we have a cylindrical pressure vessel of Young's modulus of 210 gigapascal and Poisson's ratio of 0.3, and it has an internal pressure of 3 MPa. The average diameter is 2 meters, and the thickness of the pressure vessel is 10 millimeter. We need to find the von Mises stress, the change in diameter, and the change in the thickness of the cylinder in the following two conditions. Condition 1, it's a pressure vessel with a capped ends, or a pressure vessel with restrained ends. So let's review quickly what the difference between those two problems is. In the first problem, I have a cylinder, and I'm going to pick an area on the outside wall, and this will be E1, and the vertical will be E2, and the outside will be E3. And I'm going to, so it looks like this. This is the outside wall of the pressure vessel. It's like a vessel that's full of pressure, and we need to know what the stresses are. So the stresses on this are the following. First, circumferential stress, because of the pressure, that wants to open this pipe up, this sigma in the direction of 2, so the sigma to 2 is equal to, so this is for condition 1, sigma to 2 is equal to, if this is the diameter, is equal to the pressure multiplied by the diameter. When you multiply the pressure by the diameter, you get the total force acting upwards. You divide by this thickness and this thickness, divided by 2t, you get sigma 2. And in the third direction, in the direction of 1, 1, you have, if this is the pipe, the total force here is equal to P multiplied by the area, and the area is equal to pi r squared, which is the area of this end. This pressure, or this force, will be resisted by the circumference of the pipe, and will result in a stress on the circumference in the direction of 1. So sigma on 1 in this case will be equal to the force divided by the area, and the area is equal to the circumference, or the circumferential area of that pipe, which is equal to 2 pi r t. From this, you can calculate P r over 2t, which is equal to P r is equal to the diameter divided by 4t. or you can leave it in terms of the radius, PR over 2t, and this in terms of the radius will be P. Instead of D, I'm going to put 2R divided by 2, so PR over T. And in this case, sigma 33 is 0. So I have a stress matrix that looks like this. Sigma on 1 is equal to PR over 2T, and sigma 2 is equal to PR over T, and from here I can calculate the strains. So epsilon 1 will be equal to sigma on 1 over E minus Poisson's ratio sigma 2 over E. Epsilon 1 is equal to sigma on 1 PR over 2 TE minus Poisson's ratio sigma 2 is equal to PR over TE. And what's epsilon 1? Epsilon 1 is equal to the change of length divided by the length. This gives me, because this is E1, this gives me delta L divided by the length of my pressure vessel. So this is epsilon 1. Epsilon 2 will be equal to negative Poisson's ratio sigma 1 over E plus sigma 2 over E. Now epsilon 2 has to do with once the pressure vessel expands, as the pressure vessel expands, the circumference increases, and so epsilon 2 is equal to the old circumference, so the new circumference, which is equal to 2 pi r plus delta r minus the old circumference divided by the old circumference, which is equal to delta r over r. So epsilon 2 will give me delta r over r. And from delta r over r, I can calculate the change in the radius. So this is for case 1. And of course, epsilon 33, which is epsilon 33, gives me the change is equal to delta T over T, the change in the thickness of the pressure vessel. This is for case 1, when the pipe is allowed to expand because it has capped ends, and the pressure is what causes it to expand. For condition 2, we have a different state. Condition 2. For condition 2, we have a pipe that's restrained from expanding or contracting because it's laid in the ground and the ground prevents it from expanding or contracting. I have pressure and I'm going to extract a piece of the pipe wall and assume this is E1, this is E2, and out of the plane is E3. Now in this case, the lateral constraints forces epsilon 1 to be equal to 0. Sigma 2 in the circumferential direction is still calculated from the pressure. Sigma in the circumferential direction is still calculated from the pressure. that wants to expand the pipe. P, and the stress here, which is sigma 22, is equal to the pressure multiplied by the diameter divided by a thickness here and a thickness on the other side, so P d divided by 2t, which is equal to PR over T. Epsilon 11 is 0, but I don't know what stress here. I don't know what sigma 11 is. So I know that sigma, I don't know what sigma 11 is. I know that sigma 22 is PR over T, and I know that sigma 33 is 0. For the strain, I know that this is 0. I don't know what epsilon 22 is, and I don't know what epsilon 33 is. Okay, so I'm going to utilize this condition, epsilon 11 is 0, to find sigma 11, because this is equal to sigma 11 over E minus Poisson's ratio sigma 22 over E, which gives me right away that sigma 11 is equal to Poisson's ratio sigma 22, which is equal to Poisson's ratio PR over T. So I can find the stress that prevents the pipe from expanding or contracting in the longitudinal direction. And from here, knowing sigma 11 and sigma 22, now I know sigma 11 and sigma 22, I can find epsilon 22, which is equal to sigma 11 over E minus, sigma 22 over E minus Poisson's ratio sigma 11 over E, and epsilon 33, which is equal to negative Poisson's ratio sigma 11 plus sigma 22 over E. And epsilon 22 is equal to delta R over R, and epsilon 33 is equal to delta T over T. Just if you missed what we are looking at, this is the pipe. And this is its wall. There is pressure inside. I'm looking at a piece of material right on the wall, right outside here, and I'm calling this E1, E2, E3, and epsilon 11 is delta L over L. Epsilon 22 is the circumferential strain, which is equal to the new pipe after it expands minus the pipe or the circumference before it expands divided by the circumference before it expands, which will give you delta R over R expansion due to expansion. And epsilon 33 will give me the change in the thickness of the pipe. And so given those strains, I can find delta L, delta R, and delta T. So this is it for chapter 5, the relationship or the constitutive laws for linear elastic materials. And in the next chapter, we're going to apply this to the beam approximation.